In 1820, Hans Christian Ørsted, the Danish physicist, was playing around with an electrical circuit. He intended afterwards to look at magnetism, and so he had a compass needle placed on the table. But he noticed something amazing, that when he turned on the electrical circuit, there was a deflection on the compass needle. He discovered a kind of man-made magnetism, a magnetism created by the electric current running through this wire, ever after known as electromagnetism. Ørsted noticed that when the current through the wire was low, the deflection was really quite modest. But when the current through the wire was put right up, suddenly the deflection was much more obvious. It seemed like more current resulted in a much stronger electromagnetic field. Here I'm passing the wire vertically through a piece of plastic. On this plastic I have got 5 plotting compasses, and they will show us the shape of the magnetic field. So let's switch it on, and you can see that the compass needles have all moved. Switch it off, switch it back on again. It almost seems like they're, well, the exception of that one that's a bit broken, they seem to be winding around. So now I have placed a piece of paper over this here so that we can hopefully see the field. Okay, so we're going to turn it on, just connect that. So you can see that they're going that way round. So I'm going to add my arrows like this. How do we know which way round this field is going? We use the right-hand grip rule. What we use is the thumb to represent the direction of the current. Now, if you remember that conventional current back in the day was considered to be the movement of positive charges from the positive terminal to the negative terminal, then the current is actually going to be moving up through this diagram. The curl of your fingers represents the direction the magnetic field will make around the wire. If the current was going the other way, then you can see that it would change the direction of that magnetic field. With an electromagnet, we can switch it on and off, or control the strength. Now, we can control the strength by changing the value of the current flowing through the wire, or change the design of the electromagnet. Principally, an electromagnet is a coil of wire around a soft iron core like this. So you can see that I'm going to wrap this wire around 3 times, 4 times, 5 times. And now what I will have hopefully done is amplified the strength of the magnetic field by about 5 times. And what I should find is that now, look at that, I can pick up a paper clip, just one. But I'm going to go to increase the strength of my magnet by wrapping more of this wire around. Let's keep it going. And if I keep it all going round, I've lost count of how many times I've wrapped it around now. But what I'm hoping to see is that this will make a stronger electromagnet. Here we go. Push it all down. Let's have a look. Oh no. Oh no. So here I've got probably about 15 turns on my coil, and you can see I can pick up multiple paper clips now. I've made it stronger by having more turns of wire on this coil. Let's now look at a larger example of an electromagnet. This coil of wire around the soft iron core is technically known as a solenoid. Now, what happens if we switch on the current through this solenoid is we get this magnetic field. Now, some of your compass needles may not all point at the right direction, but what we're seeing is that they're all pointing to this, the south pole that is over here. And there must be a north pole over there. If we were to repeat the exercise of moving the plotting compass, then what we would realise is that the magnetic field around this solenoid looks very much like the magnetic field around a normal magnet, with the field emerging in this shape here. just like the field around a normal magnet. And if we were asked to draw the magnetic field around a solenoid, then we would have to draw something like this, with the arrows pointing towards the south.